Hello again, and welcome back to my computer vision channel. Today we are doing the part 2 of Codetr code read. So in the previous video, we've basically talked about the transformer part of the model, at which point it is basically the same as a dyno or deformable data. Today we are going to look at the convolutional part of the model, so the auxiliary heads, how they help train encoder, how they generate extra queries to help train decoder, all of that. So let's jump right in. So this is the place where we stopped. So this is the Codetr.py file, which basically is the highest class in the hierarchy in the Codetr. So we've looked at the previous call, which is queryhead.forwardTrain, which is basically everything related to transformer. And next we're going to look at this RPN head forward train. So first let's see what it is. So it's called RPN head. Let's just find the corresponding class. And here it is. And we are calling forward train method. So we'll notice that there's no forward train method in this class. And this class inherits from anchor head. And again, there's no forward train method here. And this class inherits from two classes, one of them being base dense head. So let's go to this one. And again, finally we see the forward train method. And this forward train looks a lot like we had in transformer. So we first call the model, so the actual forward method of the model. Then we calculate the loss and actually return it. And sometimes we actually also have this proposal list with a list of proposals. So next we want this forward call, which is also defined in the same class. Oh, actually no, it's defined in this anchor head class. And so forward call receives a bunch of features, which is basically every feature level, and we have 5 of them, if you remember. And then it calls this multiply to forward single. And forward single is basically just a single pass through the model of one feature level. And forward single is defined in this RPN head. So again, we're back to the original RPN head. And here it is. So just 5 lines of code. So we have the breakpoint here. Let's continue. And here we are. So the X here is one of the feature levels. So we can see that we get both features because they are padded to the same size. So we have this batch dimension, and then image size is 116 by 100, and then 256 is the embedding dimension. So then what we do is we apply this RPN-conv, which is just one convolution, kernel size 3 by 3, stride 1, padding 1, which means that it is looking at 3 by 3 pixel area in this projected feature map, but it is not downsampling it to smaller dimensions. So after applying this convolution, the X shape is still going to be the same, right? 116 by 100. And then, rectified linear unit activation, and then this RPN classification and RPN regression. Let's look at these. So they both have kernel size 1, stride 1. So again, not downsampling, but this time they look at 1 pixel, so not 3 by 3, but just 1. And RPN CLS projects 256 dimension embedding to 9, and the regression one 256 to 36. So what is going on here? Let's take a quick overview of what is RPN. So RPN stands for Regional Proposal Network, and it actually works quite like YOLO. And this is like the first part of region of ROI model. And ROI is the one that basically pools regions. And so this is an illustration of how that works. So we received some sort of picture where this one black pixel indicates this downsampled feature map with huge embedding dimension, but it still somehow corresponds to a pixel in an image. So now what we've done in the entire model, this was the entire RPN head model. We've just basically applied one convolution. So we've looked at this 3 by 3 matrix and said, okay, this is the output pixel, for example. And now we want to do object detection somehow. So what we are going to do is we're going to say that this pixel is predicting some bounding box, right? Somewhere here, or somewhere here, or maybe even someone here. So next, what we'll need to do is to do a matching rule. A matching rule is how we connect these output bounding boxes to the actual ground truth objects. And so since we've just initialized every weight randomly, it might happen that this pixel over here in the top left corner is actually detecting something way over here, which doesn't really make much sense. Or this pixel over here in the top right corner might be detecting something way down over here. So we don't want that, and that's why we use anchors. The way we use anchors is that we match ground truth objects to the anchors, and then we say that this specific pixel has one specific anchor that it corresponds to. So here's an example. So we're looking at this black pixel over here. And well, on the picture, there are two anchors that correspond to that. But actually, in the model, there are going to be 9 different anchors of different shapes. So they might be like wide and short, or tall and narrow, and so on and so forth, right? So this guy here is going to detect 9 bounding boxes, so 9 confidence scores and 4 bounding box coordinates per this prediction, right? So let's look at one of these. So we are saying that this one bounding box prediction corresponds to this blue anchor over here, right? So then what happens? So this prediction in a randomly initialized model might still say that I'm detecting something like this, for example, like something way more illogical, something that we don't want. But I'm taking this anchor that corresponds to it, and when I match the ground truth objects, I'm looking at this anchor, and I'm seeing that, you know, this shape over here is the best match for this anchor, so this is what I'm going to match, right? So now I've selected this shape as the ground truth for this prediction. So even though the prediction is still random, it's still wild, the loss function will basically push it towards this shape that we've selected, and the choice of that shape depended on the anchor. So this is the way of basically solving this problem of something over here predicting something way down over there, and so on. So this is one of the ways it is useful. Another way it is useful is it basically allows us to say that, you know, this one pixel might actually have 9 different predictions, 9 different objects of maybe slightly different shapes. And this is quite useful in cases where you have, I don't know, a bunch of objects crammed together in a narrow space, for example. That allows you to have like one single pixel predicting up to 9 objects. And so this is the forward single method. So we've computed these scores and bounding box predictions, and we return that. And remember, this forward single call was used in this forward train. So the first call is just computing the outputs, and then we compute the loss. And the loss in RPN head is defined here, and it just forwards the call to the parent class, which is anchor head. And the anchor head loss method is here. Right, so let's continue to here and see what is going on. So I'm in this loss function call. We can see that we no longer need the actual image, the actual feature maps. We get just the CLS scores, which is, I'm guessing, an object with length 5, right? So one set of CLS scores per feature map. The same for bounding box predictions. So CLS scores number 0. That's exactly what we've seen. 116 by 100 pixels, 9 anchors per pixel, 9 outputs per pixel, 2 images in a batch. So what we also do here is we generate the anchors, right? And anchor list is also going to be of length 2, so 2 per image, and then the first image has 5 anchor lists per every feature map. And anchor list 0, 0. So that's the first feature level for the first image. That shape is 100K roughly. So this 100K is the number of pixels we had in an image. So we had 116 by 100 times 9, right? That's exactly 104K 400. Right. And similarly for other feature levels, we have slightly different number of these anchors. So basically, you can think of anchors as like flat array corresponding to each pixel. And let's actually also print out some of them, right? So each anchor is just 4 numbers, so it corresponds to some sort of bounding box. And you can see here that, so you can treat these as x, y, x, y. So this first one has the width of 44, and then the height of 22. So it's like a rectangle like this. The next one is even wider and slightly taller. So it's just the same one, but bigger. And then the next one is something else. And then this one, for example, looks like a square. So we get a bunch of different anchors of different shapes that we're going to use. The remaining parts of this loss call do look somewhat similar to the transformer loss, in that we have this get targets call, which basically solves the problem of matching. So it is going to take our predictions or take something and connect that to ground truth. It's going to do sampling to sample positives, negatives, and then we have the actual loss call, which already uses the matching result. So you can see here that we are not actually passing the predicted bounding boxes into this call. We are passing just the list of anchors. So we're not using the actual model predictions as we've talked about. We use anchors for the matching. So let's go here. So we have get targets. Let's just continue. Here it looks like we're just trying to flatten the anchors, right? So we iterate over everything. So we have this valid flag list, which basically says, you know, which anchors are actually inside the image. So then we have this cat anchor list. Let's take a look at this. Length of that is 2. Shape of the first one is 139. So this is like the flattened array of all the 5 of anchors for all the 5 levels. So we had levels like 100K, 25K, 12K, and so on. And the sum of all of these dimensions is 139K. And then we call this get target single, which gets just one image as an input. So let's continue to here. Again, we compute which anchors are actually inside, and then we select only those that are inside, right? So now the new shape of anchors is 120K, right? So we took 5 feature levels, concatenated all of them together, got 139K, then we filtered some of them out, those that are not actually inside the picture, we got 120K. And then we call this assigner.assign. So let's take a look at what assigner is. So assigner is max IAU assigner. So you can already guess that what it's going to do is it's going to compute IAU between an anchor and a ground truth box and connect them depending on that. So let's look at how it actually works. Here is the max IAU assigner. The assign method is here. Let's continue to here. And just make sure that we understand all the inputs, right? So we have bounding boxes, which are anchors, and the shape of that is 120K by 4, so this filtered concatenated list. We have ground truth bounding boxes, and there's just 3 of them, so 3 objects that we've seen on a picture. And then we're going to do the assigning, right? So the first step is IAU calculator, which basically computes intersection over union for every pair of ground truth and anchor. So the overlaps now is 3 by 120K. And then we call this assign with respect to overlap function. So let's read that one. Here's the actual logic of how we connect ground truth to anchors. So we start by assigning -1 to everything. Let's just continue to here. Our result is going to be this assigned ground truth indices object. And for now, it just has -1s, right? So the shape of this is 120K, and the shape of this object where the index is -1 is also 120K. So all are -1s at the moment. Then we compute two sorts of maximums. So one max is like, what is the maximum IOU that we get from this anchor to any potential ground truth object? And the second set is, what is the max IOU from this object to any potential anchor? And first we do negatives. So we have this negative IOU thresholds of 0.3. And we're saying that for those indices, those anchor indices for which IOU is, or max IOU from that anchor to somewhere is below this 0.3 threshold, we're going to assign that as a negative. And the index used for negatives is 0. So let's see what happens after this line. Right, so now we have the shape of unallocated objects, and that's just 600. And for those that were assigned as negatives, we have 119K, so almost all of them are negatives. So basically negatives are anchors that were not really matched to anything, and we check that the IOU to something is below 0.3. So what we're basically saying that it is like, for example, this potential bounding box, well, it does intersect with some object, but not that well. So we're really not sure what is going on in this bounding box, so we just throw that away. And for this bounding box, for example, we say that there's definitely no object here, so we're going to treat that as a negative. And as we'll see later in the actual region of interest pooling part, we need those to basically train the second part of the model that is now looking at these proposals and actually trying to say what is inside of this bounding box, and just sort of create a more precise version of the bounding box. And for training that second part of the model, we need both negatives and positives. So positives is something that actually has an object. So we have like good predictions that are going to be used by that part. Negatives are bounding boxes that don't really have object. And so we train the model to say, yeah, actually this bounding box doesn't have any object. So this is useful as well. So coming back to the code, we have a second threshold, which is 0.7. So this one is used now for positives. So if IOU is below 0.3, that's a negative. If it's above 0.7, that's a positive. And we assign the actual ground truth object indices to here. So we use 0 for negative, and so here we start with 1. So let's just see what sort of assignments we got now. So we have roughly 600K that are not assigned yet. We still have 119K that are assigned as negatives. Then we see like the first ground truth object was assigned to 2 anchors. Second was not assigned to anyone. And then the third was assigned to 4 anchors at once. And this is a problem, right? So these anchors are not dependent on the model because, right, they're basically static. They don't depend on the model. They don't depend on the picture. So if in this picture the object is not matched by any anchor, that's a real problem because we're not going to detect that object ever. And this is why we have this second condition here that now looks at the object instead. So before we looked at which object corresponding to this anchor had the maximum IOU. And now we go from the other direction and looking at like, okay, so what are the good anchors for this object? So we're looking at this ground truth max overlaps, which are indices of those anchors that are the best match for the ground truth object. And so for these, we rewrite these assignments to say that, okay, even though this anchor is a really good match to object over here, this guy over here, even it's not such a good match, this anchor is like the only guy who actually matched to him somehow. So we're going to change this assignment. So let's continue to here and then see what sort of result we got. So we still have 600 unallocated, 119K negatives, two anchors allocated to the first ground truth object, one anchor allocated to the second, and then 4 anchors allocated to the third ground truth object. So thanks to the second condition, which now looks at which anchors match at least somehow to this object, we now found some match for this second ground truth object. And we checked for this mean pos IOU here. So we would only do that if the actual IOU is above 0.3. And this is what we return. So from this assignment, you can already see the difference to transformer, because now we have more than one assignment for ground truth objects. So some of them were assigned to 1 anchor, 2 anchors, 4 anchors. In transformer, in the Hungarian match, we always had one-to-one assignment. So this is what is meant by one-to-one and one-to-many. So after we return from this function, so this was the assigner, the next line here is going to be sampler, because we now have something like 120K negatives and like 7 positives, which doesn't really make much sense. So we want to sample some of them, at least the negatives. And you can see that it's just a random sampler. You might guess what it's doing. It's just going to drop some of the negatives randomly. But let's check that anyway. Actually, let's not read that. Let's try to discontinue and actually see the result. It's probably going to be quicker. So the result has positive indices and negative indices. So we had 2 assignments, 1 assignment, and 4 assignments. So that's 7 in total. So the positive indices were not sampled. And then negative indices, out of 119K, we sampled just 249, which makes sense, right? And then we compute the loss, right? So this is basically just transformations that I'm sure are useful, but are not that interesting. Then we return to the actual loss call. So after get targets, we compute the actual loss, right? So again, we have a bunch of, and the loss now uses the actual model predictions, so CLS scores and bounding box predictions. So let's go to this loss single, just continue to here, check out the shapes. Now we are back to iterating over levels instead of images. So now we have 2 images, but just one image, one level, and same for bounding box prediction, right? We now know what these 9 and 36 stand for. We also have anchors and labels. And the labels are back to this shape of the entire sequence. So we kind of skipped that part, but now the labels that we're interested in are inverted. So 1 will stand for background class, i.e. no object, and then 0 will stand for the actual object. And we are not trying to classify objects here, so we're just saying object or no object. We do not distinguish the actual classes. And so we also have label weights. And we can check how many objects of each type there are by just doing something like this. So we have 0 objects, 0 positive labels, basically 0 actual objects. We have 100K background objects. And then for label weights, we have 193 non-zero weights, and then all the rest are going to be 0. So remember, after sampling, we had something like 7 positive objects, so 7 actual objects, and then something like 250 negatives. But that was for all levels, right? We are just doing one level at the moment, so we are going to repeat the same process 5 times for 5 different levels. So it's perfectly fine not to find positives, all the positives or any positives at this specific iteration. But the numbers are pretty much the same as we've seen before. So we have roughly 250 objects overall. And in this level, we have 0 positives. And actually, if I continue exactly 2 times, I'll find that now I have 4 positive objects, and then 12 objects overall. So, we do find these positives at some point. Now, another reason it might be confusing is that anchor sizes are different for different levels. So if we look at the picture like this makes some intuitive sense that when you look at the high resolution images, you basically want to detect smaller objects, right? So if you were to detect something like wheels, for example, right? They're small, so we want as high resolution as possible to distinguish them. But then for bigger objects, we'll sort of zoom out and we'll rely on this lower resolution feature map to detect bigger objects because, that makes sense. So this is why, for the highest resolution level that we've seen with 100K sequence length, we didn't have any matched object because all our objects were quite big. And for low resolution levels, we do see some objects. And so we have these labels, we have label weights, we have the actual scores, which are model predictions, which are now all of the same shape as labels. So actually not yet, but yeah, after this line they will be. And then we have this classification loss. Classification loss, it has weights and it's just a cross entropy loss. And then we have similar thing with bounding box loss, which in this case is L1 loss. Another interesting detail is that for box weights, for background objects, the weight is 0, which also makes sense. No object doesn't really have any bounding box associated with it, so we're not going to propagate any sort of gradient back for no-object classes for the bounding boxes. So if we come back to this Codetr.py, so the uppermost level of the model, this is where we were doing this RPN Head forward train call. You can see that it returns losses and the proposal list. And the proposal list is like the bounding boxes detected by this region proposal network, so basically proposals that are then passed to the second part of the model, which is called ROI Head. So let's take a look at how they are created. So this is in this forward train method. So the forward train, we've seen it. So we first call the model, then compute the losses, and then we have this get bounding boxes method. And get bounding boxes just forwards the call to get bounding boxes single, which is now defined in the child class. So let me just break here, continue. And I can see that I'm back to iterating over levels. And so I'm currently looking at predictions for the highest resolution level. So we have 9 anchors per pixel, back to 116 by 100 predictions. So we are basically ignoring the sampling that we had before that sampled only 250 objects. We now have all of them, all the predictions in one place here. So now what is happening is we're going to just select top 4,000 out of them for this level. And we do that to basically limit the number of potential proposals that we need. And to do that, we sort by scores. And scores are like the exact predicted classes that we had. And then we have top K, we just select the top 4,000. So let's continue to here and see how it looks like. So now top K indices shape is 4,000. So we are interested in this pre-selection of 4,000 bounding box predictions and score predictions for this level. And then we call this post-process function. And then post-process function basically performs non-maximum suppression. So now we take these 4,000 selected scores that we had and applying this function called batched NMS. So we're not going to read into that, but basically what it does is if we see a bounding box and then another bounding box that sort of looks similar, so it's almost intersecting with this one, it's really close, we think that it is just a duplicated prediction of the same object, so we just ignore that. So this is how non-maximal suppression works. And obviously we want diverse proposals to be passed to the second stage of the model, which is why we apply these batched NMS. So this is where we get the proposals from. So let me just continue to here and actually show the shape of the result. So we have losses, we have proposal list, which is an actual list, and the shape of the first element is 1000 by 5. So 1000, we selected just 1000 per all the levels. We have 4 bounding box coordinates and then 1 score prediction. And this is what is being passed to the next part of the model, the ROI Head. And this proposal list is not really used anywhere else, right? And I just want to stop here for a moment and just observe what just happened. So this was one of the heads, one of the auxiliary heads in Codetr. So as an input, it received the encoder output. So pixels processed through the backbone and then passed through the transformer encoder to improve the feature representation, which is why the RPN head model itself was really small, just one layer, just one convolutional layer that takes in pixels that were already processed a lot, and then just applies this whole machinery of matching to ground truth objects, one-to-many match, sampling, and so on and so forth. And so one result of that is that we compute the losses, and we use that loss in as the model loss, meaning that the matching that we had, the backprop coming through this original proposal head, will go back to the encoder and the backbone and all of that parts of the model and actually help train it. So it's probably better to explain it on the slide. So we are looking at auxiliary head number 1, which has this one-to-many assignment and basically connects to the loss. And so the backprop through that loss, through that auxiliary head, is going to go through this encoder, backbone, all the way to the input image. So this is like helping train this part of the model, the encoder and everything that came before it. So it's not really affecting the decoder, not yet. So we'll see how we can also improve the decoder training. But first, let's look at other auxiliary heads. So next we have the actual ROI head. So this is the second part of regional proposal network. First, let me quickly explain what is going on here. So we've started with an image, and every cell in the grid here basically depicts the pixel in the current processed feature map in the current level, right? And we have some proposals. So one proposal might be detecting sheep, for example, right? So the second part of the model is basically this old school convolutional style attention mechanism, where we select just this piece of the image, just this part, and say that now we're going to pass it through another model, which now only looks at this selected region. So we ignore everything else, ignore the background, ignore other sheep, the human here, and so on, and just focus on this one, and then just improve the detection we had. So we apply some convolutions, apply some dense layers, and then output a new bounding box prediction and a class prediction, right? So since I said that it's going to have a dense layer, as soon as we add at least one dense layer to the model somewhere in the end, the dense layer expects to see fixed size input. So this is basically what is going to happen in this ROI head. So first we have this region, and the problem number 1 that we have to solve is how to map the proposed bounding box to the feature map that we currently have, because bounding box prediction basically outputs like the actual coordinates in the original image space. But when we map that onto the feature map that we have right now, the 100 by 100 one, for example, we'll see that these pixels do not always match the actual bounding box proposals, right? So we'll always have situations where the proposal in the high resolution image, the edge of the bounding box is between the pixels in this lower resolution feature map. So we need to deal with that somehow. And there are many different ways of doing that. And currently the most popular, the most effective is called ROI Align, I think, which basically does bilinear interpolation again. So we're saying that, okay, well, we have this nearest pixel here, nearest pixel here. I'm going to just compute my bounding box edge value as this linear combination of these pixels. So this makes sure that I don't just cut off pieces of the image. I don't just pad them with something that might confuse the model. Instead, I'm saying that I'm taking this value as a Boolean interpolation between neighboring pixels, which means that I'm not going to lose any information. So this is the first challenge that is solved in this whole long science of ROI pooling. Second challenge is mapping these bounding boxes, all of which might have different shapes. So it might be like really short and wide, or it might be really tall and narrow, for example. But we want fixed size input to our dense layers, right? So we're going to map it to something that always have the same shape, so always the same square shape. And this is done with pooling. So pooling is when we have this pixel, which basically was created by taking 2 by 1 pixel map and just taking max, for example, right? So we get this pixel by taking the max of the 2 pixels. And this is always how it happens. So we take some bounding box which might have different shapes, and then we select, for each output pixel, we just take the value as the max of this variable shape input feature map. Okay, now let's try to read that in the code. So first, what is the class for this ROI Head? So it's called co-standard ROI Head. Co-standard ROI Head. So here is the definition of this. We're calling the forward train method. And so let me just break here and continue. So let's see what's happening here. So we again have some sort of input, which is a list of length 5, and the shape of the first level is 2 by 156 by 116 by 100. So this is by now familiar encoder output of 5 different feature levels of different resolutions. So we have that as an input to original proposal. We have that as an input to our ROI Head as well. And then we have the actual proposals that we get from the previous step. And so first thing we do is bounding box assigning and sampling. And the assigner class and the sampling class are by now familiar. So this is max IU assigner for assignment and random sampler for sampling. So we're going to use the same rules of matching model output, actually not the output, but the proposal to the ground truth objects to determine like which model output to connect to where. And so in the original proposal network, we connected anchors to ground truth objects. Now we are connecting proposals to the ground truth objects. And let's just continue to here and look at the shape of the result. So we have these sampling results, which is a list of length 2. The first element has some positive indices, and the shape of that is 4, and then negative indices of shape 508. And 508 plus 4 turns out to be 512, which is, I guess, not coincidental. So what just happened is we have proposals that we get from our RPN, and if you remember, we had 1,000 such proposals per image. sorted by the predicted score, predicted probability of being not a background object. Now we sample that down a little bit from 1000 to just 512, basically leaving just 4 positive connections, positive matches, and 508 negative matches. The assignment was done using our max AU assigner, which, if you remember, tries to maximize the actual AU between the proposal and the ground truth object, but also it tries to cover every ground truth object at least with something, right? So it makes sure that, we might not select any bounding box matching to this specific object on the first run, but then we try to find at least something for this object, so all the objects are covered. Next, we go into this bounding box forward train method. Let's just break here, continue. So now X is still the 5 feature levels that we had. We now have sampling results, so the actual positives and negatives that got into the sampling. Then we have these bounding box to ROI conversion, which is basically just a different format. So I'm going to skip that and just print out the shape of the result. So I'm doing this for 2 images at once, remember, and we sampled 512 total examples for each image. And in regions of interest, I just have the flattened list of all the proposals for both of the images. So 1024 in total, and then 5 numbers per proposal. So we don't need to distinguish between different images, because basically proposals are like, each proposal is, you can say, a image on its own. That's why we do this. Then we go into this bounding box forward, into here, which calls bounding box ROI extractor. So this is the thing that uses this ROI align that I was telling you about. So we can see here that we take 5 levels and only select num input levels out of 5, which in this case is 4. So we only select this for 4 levels. And then this bounding box ROI extractor has a class of single ROI extractor. So let's find that one and break there. So here it is. Let's break at the very beginning of the forward method and continue. So yeah, I'm down 1 function, just going to print out all the shapes again, just to make sure that I understand them. So ROIs is now this flattened list for both images. Fits is now this list of length 4, because we just select 4 feature levels out of 5. But other than that, the shape itself is familiar, so 100 by 100, 50 by 50, and so on. Then what we do is basically iterate over levels, and then for every level, so we have this wonderful function called map ROI levels, right? So let's continue to this one. So we're not going to read too deep into that, but basically what it does is it takes now the regions of interest, basically objects, detected objects, and maps them to corresponding feature scale. And we have the comment here that says how exactly that happens. So basically we look at the size of the object, and depending on that, we determine which level it belongs to. So after this call, we now have these target levels. Tensor, which basically says that, the first object belongs to the second level, then the second level, then the 0th level, and so on and so forth. Then we iterate over levels, and for each level we call this self.ROI layers from those regions of interest that belong to this level. So in this case, we have 1009 of them, so almost all of them belong to the highest resolution level. And then this type of this object is ROI align. So unfortunately, I couldn't read into that. I found actual code, but basically refers to the actual CPP code implementation, which is not easy to read, not something I'm going to do right now, although if you really ask for it in the comments, I might just make another code read for the source code of this one. For now, let's just continue and just see what the result is. So once again, we had features belonging to this level, which is just 100 by 100 pixels, each pixel having 256 dimensions. And we basically do our primitive convolution-based attention, where we say that it's not actually convolution-based, it's bilinear interpolation, where we say that we have detected bounding box, and let's just select that region from the image that corresponds to this bounding box, and perform our max pooling such that the output is always 7 by 7 pixels. So what we get out is now this 7 by 7 feature map, right? So we had 1009 objects on the current level. We have 256 dimensions, so each pixel in the feature map has 256 embedding corresponding to it. And then we compressed our 100 by 100 image. We selected some sort of region from that and compressed that down to 7 by 7. Even though for some of the objects it was certainly not square, but we compressed that down to the square image. And so the same process happens for all the levels, and once that is done, we have this final ROI fits object, which is now 224 by 256 by 7 by 7. So now for every region of interest, for every of the 1024, which is for both images, we have 256 dimensional embedding and then 7 by 7 feature map. So this was the bounding box forward method. So I've applied my bounding box ROI extractor, and then I have my bounding box head, which is of this shared 2FC bounding box head class. So let's break into that. So here it is. Again, it inherits from convolutional FC bounding box head. This one has forward method. Let's break here, continue, see what happens. So now X is of shape 1024, 256, 7 by 7. So it's now fixed size. Let's see which stuff actually happens here now. So we don't have shared convolutions. We don't have average pooling. We have some shared fully connected layers, right? And there's two of them. One that takes in 12K numbers and output 1024, and another one takes 1024 and outputs 1024. And we also had this flatten thingy here. So basically what happens now, we had 7 by 7 by 256 feature map, right? So that's 12K numbers in the input, 12K neurons. And then we just apply proper fully connected layer, which is the same as saying let's just flatten everything out and then apply one dense layer, or two dense layers in this case, that project that from 12K down to 1K. So this is what X is going to be. So shape of X is 1024 by 1024. So we had these 1K proposals and then 12K values for each proposal, which is like 7 by 7 by 256. And now we projected that down to 1K only, but we still have 1000 proposals. Then let's see what else is happening here. So we don't have any classification convolutions. We don't have classification fully connected layers, regression convolutions. But we have this fully connected classification branch and fully connected bounding box branch. And this one is just linear 1024 down to 81. And this one is 1024 to 320. So this is basically saying, okay, so we projected our 12K values down to 1K, and then we have two branches. One is just doing classification. Now the proper classification with the actual difference between different classes. So we have 80 classes in the Coco dataset, plus an extra class that says no object, so 81 in total. And then for each of the 80, we're going to detect separate bounding boxes. So we don't need bounding boxes for an object class, but we do need it for all the other classes. And this is what we return from here. So basically this entire function was fully connected layer and then another fully connected layer. Pretty easy. Now, if we come back up to the higher-most function, the one that defines the overall Codetr, so this is where we call the original proposal network, then the ROI Head, then we'll see that we have these positive coordinates that we extract from the result of this ROI Head call. And these positive coordinates, so we get them from our region of interest pooling head, we get them from this second model that we call ATSS, that are called ATSS in the paper. And then these positive coordinates are fed into the this auxiliary forward train, and this is basically the part that helps train the decoder, right? So let's take a look at how where these positive coordinates are coming from, right? So they're still generated in this forward train method. So here I was, and I just applied our ROI line thingy and linear layers to get the actual outputs. I want to skip the loss because it's quite obvious. So we are going to have something like L1 or GIU for bounding box and then cross entropy for the actual labels. And here is how we create these positive coordinates. So there's quite a lot of code here, but what you can get from this is basically we had our sampling results, which are completely determined by which proposals we got at an input to our ROI Head. So the sampled proposals from regional proposal network. And then for each such proposal, we get the actual ground truth labels that were used. We get the actual features that are the encoder output, basically. We get the bounding box predicted by our ROI pooling head, and so on and so forth. So for now, we just store all of that. So the result is this tuple with 4 tensors and a label RCNN. We can print the shapes of these tensors. So number 0, what was it? Just the coordinates, proposed coordinates. So for every image, for every of the 512 proposals, we have 4 coordinates. So coordinates come from this result.bounding boxes, and result is the result of sampling. So this is basically before we even applied the ROI Head. This is us basically just looking at the proposals that we had. Then the labels, same thing, just ground truth. Bounding box targets, that's the, no, this is the output of this result of applying our ROI Head, and so on and so forth. So we basically stack all of that together, we pass that further, we'll take a look at that after ATSS. So what we've just seen now, so we've seen a regional proposal head, then the second head that is called region of interest pooling, or ROI Head, which also was connected to the loss. It was using the same one-to-many label assignment as in the previous step, but once again, this is the loss down here. So we backprop from the loss from this head through this adapter, encoder, backbone, and all of that, which helps train the encoder part of the transformer. So remember, these auxiliary heads, all of them are going to be discarded during inference. So the only thing we get from this is how we train the encoder, right? And also we've saved these positive coordinates, although all the proposals actually got into that list. I don't know why they were called positive coordinates, but now we have these extra like pos chords object, which are basically just feature maps, the actual bounding box predictions, and so on and so forth, that have some good estimation of what sort of objects we're trying to detect. And they are going to be passed in at the last stage to the decoder as an auxiliary task to help train the decoder, right? Now let's look at the final head that is called ATSS. So first, I'd like to just leave the link to the actual paper here, the ATSS paper. So it came out in 2020, so it's quite late for CNN-based models, which basically shows that, despite the fact that we have transformers and all of that, we still do research on more old school convolutional-based models. They still win in so many occasions, for example, when you are constrained by resources. And this paper takes another look at what was happening in object detection. So we've talked about anchors. There are some anchor-free models, there are some anchor-based models. And this paper basically says that we did careful research. We looked at people doing experiments and then claiming that anchors are really good or anchors are not really good. But actually, if you just take a careful look at all the differences between different models in different times, what you see is that if you control for stuff like how many positives and negatives you pass at every iteration, then it doesn't really matter if you have anchors or not. But people didn't control for that. People used like different schemes for that, and that's why they saw that this anchor-based model works better, because they had different scheme of selecting positives. So what they did is they basically controlled for that and proven that it doesn't really matter that much. So what you need to carefully look for is the actual positive and negative sampling, and this is what we'll see a lot in the code. So like main differences of this model will be in how we get and sample the targets. Another interesting thing here that puzzled me for a bit, that is explained in the paper, is called centeredness, which solves similar problem to anchors. So remember, we talked about anchors in the context that, let's say, this output pixel, what's stopping it from detecting something way over here, right? So in anchor-based models, we have anchors to basically bound the object to the pixel that is actually close to it. In ATSS, they introduced a different concept called centeredness, which says that, having a pixel over here, let it detect an object, but also output a number that says, how far the object is from the center. And then we just add a loss to try to minimize that number. So that naturally sort of helps predicted bounding boxes for a certain output pixel to actually be close to this output pixel itself. So this is like the second way of solving the same problem. As we'll see in code, the ATSS variant actually used in Codetr uses both centeredness and anchor boxes. So this is quite interesting. So let's take a look at the code. So we're back to the uppermost function called Codetr.py, which had regional per portal network, ROI Head, and now this one is called the box head. And the type of that is ATSS Head. So let's find it. Here it is, the ATSS Head. We can see that it inherits from the anchor head. We've actually seen that one before. So this version of ATSS is going to contain anchors. So the method that we call is forward train. If we look for it, again, it looks pretty familiar. So we have this self call, which just invokes the forward method. Then we have loss and this bounding boxes thingy that returns the proposals. I'm not sure if this is the same one that is used in these post coordinates, but let's see. So let's look at the forward method. The forward method just calls multiply to forward single, and here is the forward single, right? So let's see what's going on. So X is now familiar 100 by 100 feature map that came straight from encoder. And then we have self.cls convolutions, which is just one convolution, 256 to 256, kernel size 3, stride 1, padding 1, which means that it's not going to change the actual resolution of the image, and the actual embedding dimension, it just basically project the image to the same size. Then self.regression convolutions, again 256, 256, kernel size 3 by 3, stride 1, padding 1. So again, this is going to just create the image of the same dimensions, same embedding dimensions, same pixel dimensions. Then we have this ATSS.cls, which is again a convolution, but now we project 256 embedding to 80 class predictions. And then we have ATSS regression, 256 by 4. So now instead of 80 classes, we have 4 bounding box coordinates. And finally, this self.ATSS centerness, which is again convolution, 2D convolution, which has just one output number. So this one looks really close to regional proposal network, the first head that we've seen. So it takes an image, feature map after the encoder, and then just applies convolution in such a way that basically for every pixel in the input, you get some pixel in the output, and then we try to connect all of these outputs to the actual ground truth objects. So after the forward call in ATSS, we have this self.loss call, and it generates anchors in actually the same function that we didn't read from this anchor head, and then it calls this self.getTargets method. So first let's print out like what are the anchors. So it's a list of length 2. First element of that has length 5. And then first element has the shape 11K by 4. So now for every image for each of the 5 levels, we now have this set of anchors. And in the first AUX head, we had like 100K total anchors, 9 per pixel. Now we had just 1 per pixel. And so we had 116 by 100 picture. So now we get 11K anchors. And we can just print out the first 10 of them and see how they look like. So if you stare at these coordinates for long enough, you'll notice that they're all square. So in RPN head, you had like rectangle anchors that are more wide than narrow and more narrow than wide and so on, and then square anchors and so on. So totally 9 anchors of different shapes per pixel. Now we all have pixels of square shape that basically just try to tile the entire space with the anchors, which seems to be enough in ATSS case. And then we call this getTarget method. So getTargets, once again, just forwards the call to getTargets single, which calls this assigner.assign and sampler.sample. So let's continue to here and just see what the assigner is. So assigner is ATSS assigner, and then sampler is pseudo sampler. So let's go to the ATSS assigner. Here it is, and break at the very beginning of this assign method. So what we get in input is the bounding boxes for the anchors that we use and the actual ground truth bounding boxes. Let's just continue until we meet something interesting. So we compute overlaps. So overlaps are IUUs between every pair of anchors and ground truth objects. So in our case, we have 3 ground truth objects. Here they are, the dog, umbrella, and the person. And so we compute the IU between each of them. Then we compute center distances between the ground truth object and anchors. So then we iterate over all levels, and we want to select top K anchors to match, right? And top K in this case is, so top K in this case is just 9. That's interesting. We just need 9 objects. And then we compute this top K function from distances per level. So we're going to select 9 objects based on the center distance between ground truth object and the anchor. And we append that to the candidate indices. So then I would say these 2 lines are crucial for ATSS. So we had overlaps, which is now the IUU between the candidate, the anchor, and the ground truth object. And now we compute the mean over these candidates and the standard deviation. And remember the shape of this is 45 by 3, so 9 per level. right? So we compute mean and standard deviation over these 45 candidate anchors, and then we come up with this IU threshold per object, per ground truth object. So that's an array tensor of shape 3. So for each of the ground truth objects, we basically now have roughly 15 candidates for each. And then we decide which proposal, which anchor is positive or not, based on the overlap, the IU. So basically we've selected just 45 total anchors based on centeredness, right? Then out of those selected, we compute IU, mean and standard deviation, and then we use that to dynamically adjust which of these candidates are going to be positives and which are going to be negatives. And this is like the crucial piece of ATSS Head that now dynamically selects positive and negatives. And this is pretty much it, right? So we also have this is in ground truth check that checks that the actual center of selected bounding box is inside the ground truth object. So it can get quite far, but at least the center is inside. And then this is what we return basically. So this is pretty much it regarding ATSS, right? So we have pseudo sampler as well, which is pseudo because the actual sampling was just done in the assigner code. So I want to also stop one level up before we return from this ATSS loss function, because it returns these anchors, labels, bounding box targets, and all of that are then going to be used in the decoder training. So I'm just going to print like what is ORI labels, original labels. So that's a list of length 2. The shape of the first list is 15K. So we basically have all the proposed anchors, all the valid proposed anchors for all the levels. And we can also check which ones of them are actually positive and negatives. So the AT class is the special background class, and you can see that most of the anchors that we used are going to be just negative, so background class, and then everything else is positive, and we have just 27 positive objects. And we have original anchors, we have original labels, we have original bounding box targets. So notice that the actual output of the model is not used here. So what is used here is which anchor got matched, which label it was matched to, and the bounding box coordinates for that ground truth object. So that is what we are going to pass in this post coordinates, which is then going to be used in the decoder, in the special auxiliary pass of the decoder to improve decoder training. So coming back up to the Codetr.py, so we've just seen this bounding box head, which is ATSS, and then we're going to iterate over positive coordinates and have this self.queryHead.forward train aux. So we have two positive coordinates, right? So one from region of interest pooling and one that we've just seen from ATSS. So query head is the one we've seen with transformer. So it's a codeformable data head, codeformer data head. So let's find this forward train aux function. So it calls these auxiliary targets from this post coords object and then forward aux. So let me break here. I'm going to skip a lot of code on different transformations that were used because there's so many code and it doesn't really do much, and just focus on the actual transformer here. So we are in the very beginning of codeformable data head. This is the beginning of object detection part of the transformer, and we can check like what is used here, right? So auxiliary labels, for example. So you see that there's just 2 by 13 of them, so 13 per image. So we've got some sampling going on. Nevertheless, we still see a lot of background objects and then some foreground objects, some actual objects used as these auxiliary queries. And so you can see that in the actual forward aux call, the actual labels and bounding box weights and bounding box targets are not used, but aux coordinates are used, and they're just passed to this transformer forward aux. So let's go to the transformer. The type of the transformer is codeformable data transformer. So here it is. Let's just break here. So we're back in transformer. We've seen the actual transformer in the previous part of the video. So we have like features for all the levels. We have masks. So by now we've already performed the encoder stuff. And now we can just quickly trace like where are these anchor coordinates are actually used, right? So first of all, we have this top K and then positive anchors, and we select top K coordinates before activation as these positive anchors, and then we use that to create reference points, and also like from these top K coordinates before activation, we also call this get proposal positional embed function. So if we quickly look into that, this is the sine cosine embedding, right? So basically what is happening here, a quick reminder of what was happening in the transformer in the normal detection part. In the normal detection part, we were setting up the queries, and there are basically two ways to do that. So one way is to just initialize them statically, like 300 queries, not dependent on the actual image content at all. Second way to do that is to take encoder outputs and make encoder detect some objects, basically. So out of like 20K sequence outputs of the encoder, let's just make every sequence output detect something, so class and bounding box predictions, and then we apply this top K function that selects top 300 based on some sort of rule, right? And the rule is in the first case was the actual predicted score. So the higher probability of actually detecting the object here, the higher the chance that we take this sequence output as our query. Now here, instead of proposed queries from the encoder, we have these anchors that are like proposals that we've got from our ATSS head, from our ROI heads, so from auxiliary heads, basically. We use them as reference points, which are centers of attention for deformable attention. We also apply sine cosine embedding to create the actual query input. So we had four numbers, x, y of one corner and x, y of another corner for the bounding box, and we use that to expand it into embedding of dimensions 512, and then that is used at the actual query embedding that is then passed to this decoder, right? So we split that into query pos and query, and this is what is passed to the decoder. And the actual decoder code, decoder call itself is exactly the same as in the first part of the model. So coming back to the diagram, so we got proposals, bounding box proposals for two auxiliary heads. Then we basically set up some sort of queries for the decoder based on that by taking four bounding box coordinates, using them as reference points, and also expanding them into 512 dimensional positional embedding. And that's how we come up with this query input. And then we pass it through the decoder. So if I just continue to the start of this decoder call and just print the shape of this, right? So on the first stage, we had 300 queries. Now we have just 13, right? So for each of the two images, we have 13 queries, 256 embedding shape, and that is passed as the query input for the decoder. Finally, coming back to our route with Codetr.py, the forward train aux call, if we go back to it, so it had get aux targets, forward aux, and then loss aux. We can quickly look into loss aux, but basically it will just apply the loss single and loss single. It already has the CLS scores and labels, and it will just apply the actual CLS loss, right? So it is not doing any matching. So normally, if we come back to this forward aux, normally we would have get targets and then forward, or forward and then get targets. In the get target method, used Hungarian matching loss in case of the transformer. Here we're not using any Hungarian matching because the matching was already done for us. So we just take the anchor coordinates and the corresponding ground truth coordinates that we got from our auxiliary heads, and then just use them for the loss. Let me show that on diagram. So basically we've created these auxiliary queries, right? So in normal part of the decoder, right, no matter how we came up with these queries, we don't really know where they connect, right? Which is what we want during inference. That is why when we train the thing, right, the output, we don't know which ground truth objects they connect to, right? So to solve that, we have this one-to-one set matching, aka Hungarian matching loss, that will try to connect them somehow and then find the best connection such that the loss is minimal. Now, this thing is unstable. This thing can lack signal. This thing can match different ground truth objects to different sequence elements in different epochs. And then in this auxiliary part of the decoder, we know which ground truth object to match to, right? So they just directly matched without the need for Hungarian match loss. So this is why it works better. And then another question you might have about why does that work at all, right? So we basically, during inference, we want the decoder to do this, right? Because we don't know the ground truth objects. And so to improve the decoder, we train it to do this, right? So how does that help? And it helps because the task we're asking the decoder to solve here is actually really similar to this task, right? So in this task, we have some proposals for the bounding boxes, for the classes that are encoded in this query embedding and reference points and so on. And then we ask it to take these initial crude proposals and then predict the actual bounding box coordinates, right? So to get the better estimation of where the objects are. And here we're actually doing the same, right? So here we have anchor bounding box coordinates as input, encoded into the embedding as well. And then we asked the decoder to take these anchors, which are, again, just crude estimation of where the objects are, and then to basically improve on this detection. So the task being solved in this inference case and in this auxiliary case is actually pretty similar, and that is why using these auxiliary queries to train decoder actually helps it perform better on its main task. So this is it regarding Codetr. I hope this was useful. I hope I've answered most of your questions. I hope to see you soon.